Welcome everybody to the second episode of School of SuperAdobe, a brand new platform dedicated entirely to free earthbag education. In this episode, we'll be covering how to draw the basic shape of your first SuperAdobe Dome. We'll be building on and referencing information that we shared in episode 1, so if you haven't watched that one, head over to schoolofsuperadobe.com and hunt down episode 1 in our education tab and give it a thorough watch. This is course number 1 from School of SuperAdobe and focuses solely on how to build a SuperAdobe Dome. The specific dome shape synonymous with SuperAdobe is achieved using 2 compasses. They're often made from chains in the real world, but in this exercise we're going to be mimicking those exact chains. The measurements and geometry of the drawn dome versus the constructed real-life dome is really very close to each other, if built precisely. So many decisions and design features can be very accurately represented and predicted from these simple early drawings. So what you'll need for this exercise is a pencil, a few pieces of paper, an eraser, a ruler, and a compass to fit your pencil, and an hour or more to have a solid play with these ideas. I really encourage all of you to follow along at home because this can be a really daunting and confusing aspect of dome building, but if it's understood in these very early stages, way before you step on site or pick up a shovel or pick up a bag, it will instill so much more clarity and confidence in you as a builder once you do make it to site, and ultimately will help produce a better end product. In this exercise, we will be drawing to scale. Now, although this is potentially a large concept to grasp for the beginner, it's so important to accurate design, budgeting and material purchasing, and ultimately project success to be drawing to scale even in these early stages. That being said though, I didn't design and draw my first few domes that I built. They're quite basic buildings, and I also just didn't have the skills or the foresight to be able to do that yet. So the first couple domes that I built, they weren't designed or drawn, but it will make your whole process and workflow just so much more informed, so much clearer. You'll have a lot more confidence, and also you can discuss things so much clearer with the people you're building with, your clients, and also yourself. So I really do encourage doing it even at this early stage. Scale is represented by a ratio, which is written as 2 numbers separated by a semicolon. The first number represents the unit drawn on the page, and the second number represents the amount it needs to be multiplied to become accurate in the real world. Drawing to scale means that what is built in the real world and what is drawn have a direct relationship to each other in reference specifically to their measurements. In our case, the building will be large and the drawing will be small at a direct ratio to each other. In some engineering or electronic projects, the scale is the opposite, where the drawing is large, but the part being built is often very small, like a microchip or a tiny watch gear. Now, experience will teach you how to choose the correct scale ratio so that your drawing will not be too small or too large on your piece of paper. For example, in metric first, which I'll be mainly focusing on, common architectural drawings are drawn at either 1:5, 1:10, 1:20, 1:50, 1:100, and all the way up to 1:5,000 or higher for large-scale development projects. A common scale for imperial, for example, would be 1/4 of an inch equals 1 foot. Now, although this imperial example is in fact a ratio of 1:48 scale, it isn't written or discussed in that way. So unfortunately, the 2 systems are quite different in the way they are executed and discussed in the real world, albeit they rely on the same fundamental principle of a scalable ratio. So for that reason, I won't be sharing too much on the imperial system as it's not what I've learnt. It's not what I'm familiar with, but I will link a lot of resources for you to investigate if you'll be working in the imperial system. So taking 1 to 50 as an example, 1 millimeter on the drawing is equal to 50 millimeters in the real world. The same thing applies to centimeters, meters, or kilometers. 1 centimeter on the drawing is equal to 50 centimeters in real life. Now, when using the metric system, the unit isn't locked to any specific measurement and is infinitely scalable, but in imperial, it is locked. So how do we choose a scale? We work backwards from our real-life measurements and onto the paper at this stage. To figure out our first measurement, we will decide on the internal diameter we want our finished dome to be. So let's say, for this example, I want to build a 4 meter internal diameter dome, which is close to 14 feet. That is the measurement at springline and floor level from one internal wall across the center of the dome to the opposite internal wall. Let's experiment with our first scale, just chosen at random, 1 to 200. We'll be working with the second number in this scale, which is 200. We take our decided internal diameter, 4 meters or 4,000 millimeters, and divide it by the second number, 200. So 4,000 millimeters divided by 200 equals 20 millimeters. So if we choose this as our scale, we would end up with a tiny 20 millimeter wide drawing of our future dome. Although it would still be accurate, it isn't very helpful to us if we want to look at it closely or begin adding drawn-in furniture or easily show it to other people or to our clients. It's just too small. So let's try the next one down, 1 to 100. Same thing, 4,000 millimeters divided by 100 equals 40 millimeters. Again, a 40 millimeter drawing is not too helpful, although it is an improvement. So let's jump all the way down to 1 to 20. Same again, 4,000 millimeters divided by 20 equals 200 millimeters. As this sits on an A3 piece of paper, it is a very comfortable working size without being too large or too small. So let's choose this very common scale to work at for the rest of this exercise, 1 to 20. To explore my point further though, if we did go down less than that, say 1 to 5, 4,000 millimeters divided by 5 equals 800 millimeters, that would be too large to draw on a piece of paper. It's almost a meter. So in summary, choose a scale which gives you the largest comfortable drawing size based on the piece of paper that you're working with. Now that our scale is decided, let's get into the nitty-gritty. So 4,000 millimeters at 1 to 20 equals 200 millimeters on the page. So let's draw a horizontal line at 200 millimeters long. This is our internal floor diameter. It's a good time to mention also that this first drawing is what's called a cross-section or an elevation. It's called a cross-section because it's like we've literally cut the building in half along one specific plane, in this case directly across the center point of our dome. And we're looking at the building from a side-on view, like we're standing at ground level looking horizontally at the building. It's called an elevation because it shows us exactly that, how the building rises up out of the ground and only expresses to us its points of elevation and its width, and it tells us nothing about the depth. I'll now reference the first general rule from episode 1, which was our finished wall width should not fall below 10% of our internal diameter. Therefore, our filled and tamped bags must not be less than 400 millimeters. Based off the shared common measurements between a filled bag and an unfilled bag shared in episode 1, we would choose a 450 millimeter bag to fill out to 400 millimeters. To find the right bag to purchase, take your final wall measurement, which is 10% of your internal diameter, and add 50 millimeters or 2 inches. For example, I need a 400 millimeter final wall width, so I'll add 50 millimeters equaling 450 millimeters, which is the size bag I'm going to order. In Imperial, I want a 16-inch final wall width, so I will add 2 inches, which equals 18 inches, which is the size of bag I will order. It's okay to order a bag a little over this dimension, but if you go too much over, you'll end up losing efficiency on the build because you'll need to put too much extra material in to fill the bags. So only do this if you specifically want very thick walls as part of your design brief. Otherwise, it becomes detrimental to the timeline and also the budget of the build. It takes longer to fill the bags and you've got to put more material in them. But back to our drawing. So we've got our internal diameter drawn. Now let's add the walls. So same as before, because we will always work in the same scale for the entire drawing, we take our 400 millimeter final wall dimension and divide it by 20. 400 millimeters divided by 20 equals 20 millimeters. So we'll draw 2 horizontal lines at 20 millimeters long and mark the beginning and end of these lines. Leading on from this, we'll be introducing our compass. The compass ultimately is a tool which draws circles or only parts of circles, which are also called arcs. In this exercise, this compass will be mimicking our fixed compass in real life and drawing the exact same arc as happens on site. And this is why these drawings are so helpful and accurate. Compasses are adjustable in 2 ways. Every compass is a little bit different, but this is basically how they function. One way is opening them up like this, which expands that measurement, which is actually the radius of our circle. So by closing it or opening it, we're closing our radius or expanding our radius, getting a longer radius, so therefore a larger diameter circle. And adjustment number 2, not all compasses have this, but most do, is moving this pencil up and down. And the reason we want to do that, we want to have the lead of the pencil basically in line with the sharp point there, because that gives us an ergonomic way to swing out those circles. So that's basically how you adjust them. So take your compass and place the sharp point on one of the external wall points. Then place your pencil end on the opposite internal wall point. Draw an arc going all the way up and past the center point of your dome. It doesn't matter where you stop, just make sure you draw past your center line. Now, do the exact same, but on the opposite side. Sharp end on the outer wall point and pencil on the internal wall point. Draw your arc up until it intersects with the first line. And that is the exact geometry of the inside surface of your SuperAdobe Dome. How rad is that? Now let's draw the outside. So this is where the drawing of the dome can take one of 2 directions. Number 1 is accurate to the real world, or number 2 is a more balanced and visually appealing one once it's drawn and it's on the paper. So to be most accurate to the real world, place the sharp point on the internal wall and the pencil on the opposite external wall. Draw up and past your center line. Do the same for the opposite side. This will mimic the tapering in of the bags as they step inwards and become less tall. If you'd like, though, a more balanced looking and kind of robust drawing, which is a little taller than the real life version, place your sharp point on the external wall point and your pencil on the opposite external wall point. And repeat this on the other side. This will give you a taller, more full wall dimension, and it often looks a bit better on paper and when you're displaying it or showing your drawing to clients or other people. So you can make that decision if you want. Now, instead of putting information into our drawing, we'll now be discovering new and accurate measurements from our drawing, which will be very accurate to the real world. First, let's measure the height. We're going to find our center point, which is 100 millimeters, because our internal diameter is 200 millimeters in this drawing. And now we get our ruler and place it from floor height of our dome, and we measure all the way up. So I've got 182 millimeters. To find out what that measurement is in the real world, we simply multiply it by the second half of our scale. So we use the same 20 which we used before. Again, we always stay within the same scale for every equation within one drawing. Once it's decided, you will never change for that whole drawing. So 182 times 20 equals 3,640 millimeters, or 3.64 meters from floor level to internal apex. Lastly, for this exercise, I'm going to draw in a scale model of myself so I can see how well I'm going to fit in the inside space of my dome. See if I need to make any adjustments, if I need to make it taller, if it's going to be too small to be habitable, whatever. You can use this same technique to not just put in a scale model of yourself, but you can draw in scale versions of maybe a fridge or some furniture or a bed or really anything that you want to put in the space, so that you can start at this early stage to see exactly how those things are going to fit in the space and whether you do need to make adjustments, because once you've started your dome, it is impossible to make adjustments of the size. So we take my height, which in the real world is about 190 centimeters, which is 1,900 millimeters. We take that and we divide it by our magic scale number, which is 20. So 1,900 divided by 20 equals 95 millimeters. I'm then going to find 95 millimeters on my ruler, draw a line, and then draw a nice little happy version of myself. So I can see now really clearly from this drawing that I'm going to almost be able to sit on my own shoulders before my head hits the apex of this dome. That's really, really good to know, because before doing this, I had no idea whether it's going to be cramped or whether I'm going to be crouching or anything like that. And as I said, you can do this for anything at all at this stage. You can put a fridge over here, you can put in some furniture that you already have, you can just Google the dimensions of a bed, do the same reduction based off our scale, and draw in a little bed over here to see how far your bed might come into the space or anything like that. So it's really, really, really powerful, even though it's so simple at this stage. Our next step in this exercise is to draw the dome from above. This type of drawing is officially called a plan view as opposed to our previous elevation view. But it's also colloquially referred to as a bird's eye view, as it's showing us exactly that, what a bird might see if it flew over the top of our building and looked down. It's also sometimes called a floor plan view, and it's normally showing us everything that will be making contact with the floor. In our previous elevation plan, we mimicked the fixed compass from our real-life on-site chains, but in this view, we're going to be mimicking our center compass only. We'll be using the same pencil compass as our elevation view, but we're going to be drawing complete circles this time, instead of just an arc, which is just a section of a circle like before in our elevation drawings. We're going to be using the same 1 to 20 scale as before, and also the same example of a 4 meter or 4,000 millimeter diameter dome. We start by making a center point anywhere within the middle of the page. The main difference between the on-site center compass and our on-page pencil compass is that with the pencil compass, we're deciding the measurements in millimeters based off our imagined dome's diameter, whereas on site, our center compass is determined and adjusted every single row by mimicking the information given to us by the fixed compass, not a decided measurement taken off a tape measure every single layer. So it's good for me to start discussing this so that you can begin to understand the differences and the way the two compasses operate. Just as our elevation drawing was of only one single plane or slice of our building, our plan view is also of one single plane or slice. The view that's most common is what you'd see at floor level, which is also our spring line of our dome in this exercise. The reason this plane is most commonly chosen for designing domes, but also any other type of standard house or building, is that it can display the most useful information like where furniture will be, where doorways are, and where services will enter through the floor or the concrete slab. You can imagine if we took a slice from up in the roof cavity, how useless that information would be to the common person or to the clients wanting to eventually live in that house or dome, because you just end up seeing things like rafters and AC ducting and things like that. So it's not terribly useful or interesting. So that's why this floor plan is most common, because it's most easily understood by the common person. So we take our desired internal diameter of our dome and we exactly halve it to determine our radius. So 4,000 millimeters divided by 2 equals 2,000 millimeters in our real life dome measurement. We use the same equation as before, 2,000 divided by 20 equals 100 millimeters. So we measure out from our center point 100 millimeters and make a small mark. We then take our compass and place the sharp end on our center point and pencil on our 100 millimeter mark. We then draw a complete circle. This is our exact internal dome layout at a 1 to 20 scale. To determine our external wall measurement, we take our wall width, 400 millimeters, and divide it by 20 as we did before for our elevations. This equals 20 millimeters. Make a mark 20 millimeters out from our internal diameter. Again, take the compass and place the pencil end on this external measurement. Draw a complete circle. This is now our external wall placement. We will now be placing a piece of furniture in here, so let's choose a bed. From a quick Google search of standard double bed measurements, I found 1350 by 1880 millimeters. Same as always, we will take these measurements and divide them by our scale of 20 to reduce them down to the correct size for our drawing. So 1350 divided by 20 equals 67.5, but let's just round it up to 68. And 1880 divided by 20 equals 94. So I'll draw a rectangle measuring 68 millimeters wide and 94 millimeters long. I will first cut this out with scissors so that I can move it around more freely in the dome and find out how it's going to fit best. I can also do this with other furniture like a fridge or a wardrobe or anything at all that I'd like to move around the space. And from this, I can either trace my piece of paper or redraw it onto the plan permanently. To touch briefly on the imperial system, I don't want to leave you guys out. As I mentioned, the two systems are quite different in the way that they're executed in the real world and drawn on the paper. And just let it be known that I have absolutely no experience working with the imperial system, all right? So as a quick kind of explanation of what I can understand of it, if we want to build a 14-foot internal diameter dome, which is very close to our 4-meter example, the drawing and the compass system is still exactly the same. It's just our measurements that we alter and how we find out those measurements. So a common and similar scale to 1 to 20 from the rest of the episode is approximately 3/4 of an inch to 1 foot. As I mentioned earlier on in the video, the imperial system is locked to set measurements as opposed to an open ratio like 1 to 20. So you must always be thinking and referencing these exact set measurements, which is an added level of complexity and confusion in my mind. You're also working with fractions all the time, which is just a total headache to try and juggle coming from a metric point of view. So how about we start a comment wall below and let's try and figure out what the better system actually is. So our 14-foot diameter dome will become 14 times 3/4 of an inch, or 14 times 0.75, which equals 10.5 inches, or 10.5 inches. So take this measurement, 10.5 inches, and mark it on your page, just as we did before with the metric measurement. You can see that the equation is different than in metric and becomes even more confusing when we try to figure out the wall measurements in inches. So that's where a scale ruler can come in handy. These are architectural rulers which have the equations already solved and marked out on them, and they're useful for both drawing but also reading and interpreting plans and taking measurements directly off printed plans. But as I wanted this exercise to be accessible to everyone, I chose to show how to use a standard ruler, as this will be much more common. I want to touch briefly now on the geometry of these domes and how beautiful and powerful this shape actually is. Now, these domes are some of the strongest buildings you can build for a few reasons. One of them is it harnesses the power of the arch. Arches have been used for thousands of years and they are inherently self-supporting, which is a key aspect to their strength. A dome is just an arch ultimately rotated 360 degrees, which creates this indivisible amount of arches within the dome's walls, which are always supporting each other. Nada Khalili and his students at Cal Earth, they borrowed the compass system from traditional Adobe brick dome and vault construction, and they applied it to the SuperAdobe bags. So although the SuperAdobe method is groundbreaking and incredibly creative, the compass system and concept is many thousands of years old. The elevation view of a dome is based off the lancet arch, which is incredibly close to an ancient form called the Vesica Pisces, which is also the second step in the flower of life if you want to get crazy about it. It mimics the forms found endlessly in nature, like the top of an egg or the structure of some cells. Harnessing these shapes and forms is part of why these domes are so incredibly strong and also incredibly beautiful and quite mystical, I think. They echo the stunning beauty of the architecture of Nada's homeland of Iran and the Middle East, and is an amazing rabbit hole if you'd like to go down it, which is ultimately what my life has become. So I hope you too can sense and tap into some of this beauty and timeless design. So that's it for this episode. I hope that you've learnt a few things, and we're going to continue to develop your drawing skills over this course and do a few more exercises to show you how to best design your domes. Now, as always, please head to www.schoolofsuperadobe.com and sign up to our mailing list so we can stay in more constant contact. And also, please do give us a like and a follow on Instagram, Facebook, TikTok, and YouTube. So until next time, peace, love, and bags, everybody. Bye-bye. Bye.